Inductor, a device that stores energy in a magnetic field. It consists of an insulated wire wound up into a coil known as a solenoid. Inside this solenoid is a material known as an inductor core. This can be any ferromagnetic material such as iron or cobalt, but it could also be just a gap filled with air. When current flows through the inductor, a magnetic field builds up inside and around the inductor. This field is what stores the energy, and when the current is removed, the energy is released back into the circuit as electrical energy. All inductors have a property known as inductance, and this measures how well an inductor opposes any change to the current flowing through it. We shall discuss more on this later in this video. Inductance is measured in a unit called the Henry. Commercial inductors have values ranging from nanohenry to around 50 henries. Let's look at how inductors work in more detail. When current flows through a wire, it creates a circular magnetic field around the wire, and this field has a direction which can be clockwise or anti-clockwise depending on the direction of the current. When the current increases, the strength of this field increases and vice versa. When this wire is made into a solenoid, the current now creates a magnetic field similar to that of a bar magnet, and this field exists both inside and outside the solenoid. When you connect a solenoid to a DC power source and close the switch, current starts to flow through the circuit. The current starts at 0 and increases rapidly to reach some maximum value. As the current increases, it creates an increasing magnetic field in the solenoid. As the field grows, it creates a changing magnetic flux through the solenoid itself, and according to Faraday's law, this causes a voltage to be induced in the coil, known as a back EMF. Lenz's law tells us that the induced voltage opposes the voltage due to the battery. The back EMF thus opposes the increasing current, causing it to increase at a continuously decreasing rate. This means that the magnetic field will also start to increase at a decreasing rate. Because of this decreasing rate of change of the field, the induced voltage also decreases until it reaches 0, which happens when the current and magnetic field are now at their maximum values and are no longer changing. The inductor is considered to be fully energized. This phenomenon is known as self-inductance, and due to this property, solenoids are often called inductors. In reality, all conductors exhibit some inductance, even straight wires, though it is to a less extent. So generally, an inductor behaves like a current-sensitive resistor. It only resists during changes in an increasing current. Otherwise, it passes current as if it were a wire. The inductor resists current the most when the increase in current is most rapid. The voltage across an inductor is always equal to the back EMF in said inductor. It is maximum during the greatest rate of change of current and is 0 when the current is steady. When the switch in the previous circuit is opened, current rapidly decreases to 0 since there is no longer a voltage from the battery to drive it. This means that the magnetic field of the inductor also collapses rapidly, again creating a changing magnetic flux in the inductor, thus inducing a voltage in it. From Lenz's law, this voltage opposes the decrease in current, trying to maintain it at the same value, thus causing it to reduce relatively slowly. In this way, the inductor acts as a power source by dumping all the energy it had stored up back into the circuit. The maximum voltage in the inductor is induced when the current is changing most rapidly, which is at the moment when the switch is opened. In reality, at the moment the switch is opened, the rates of fall of the current and magnetic field are so high that the induced voltage manifests as a huge spike. This spike is so large that it creates a big enough electric field across the contacts of the switch to cause a spark to occur. Unlike with capacitors, which can retain their energy in the electric field when the power supply is removed, once an inductor is disconnected from the power supply, it releases all the energy stored up in the magnetic field. This is evident in some electric motors, which cause a huge voltage spike to occur when you turn them off. This is because, at that moment, all the energy stored up in the magnetic fields of the coils is dumped promptly, inducing a very large voltage in the process. If proper caution is not taken, these spikes can damage other devices connected to the circuit. The energy stored in an inductor is given by this equation, and the induced voltage at any point during the energization of the inductor is given by this equation. Inductance plays a big role in predicting the behavior of an inductor. Inductance depends on several inductor parameters such as the coil shape, number of turns, and the core used in the inductor. Inductance is calculated using this formula. A ferromagnetic core immensely increases the magnetic flux density, thus increases inductance as well. It achieves this by aligning its domains with the magnetic field of the coil. Thus, the two magnetic fields line up and reinforce each other, resulting in a stronger field. A ferrous core can augment the field strength of a solenoid by up to 1,000 times. Here is the schematic symbol for an inductor. When several inductors are connected in series, the resultant inductance is the sum of all the individual inductances in the network. When inductors are connected in parallel, the overall inductance is related to all the individual inductances by this equation. It tells us that for inductors in parallel, the overall inductance is less than the smallest inductance in the network. Inductors can work under DC or AC. Just like capacitors, inductors exhibit some very useful properties such as inductive reactance when connected to an AC supply. We shall discuss more on this in a future video. Inductors are essential in electrical and electronics equipment. Some of their uses include filtering of unwanted voltage ripples and storing energy in power supplies, construction of inverters, converters, and transformers. In signal processing, inductors are used to filter out unwanted signals at certain frequencies. If you enjoyed the video, please leave a like, comment, and subscribe. That's it for how inductors work. Thank you for watching.